All right, so this lesson we're going to start looking at two-dimensional collisions. In the previous lesson, or really previous two lessons, we discussed kind of head-on one-dimensional collisions. Things can move to the right or to the left. But in the real world, most collisions are two-dimensional collisions or possibly three-dimensional collisions. Things can move to the right, to the left, up and down, or to the right, to the left, forward, back, up and down. So we would need to make use of the fact that momentum is a vector to work these types of collisions, that we would need to break down into x component, y component, and z component if it was a three-dimensional problem, and look at how momentum is conserved in each direction to solve these problems. As long as the system is isolated, that the net external force acting on the system is zero, then momentum is conserved in two and three-dimensional collisions. So let's work a two-dimensional collision problem and see how this works. Here I have a picture on the right that shows a collision between two balls on a flat table. The first ball, which is the red one, has a mass of 0.15 kilograms and is moving initially at a velocity of 0.9 meters per second at a direction 50 degrees to the right of the negative y-axis. So it's moving down and to the right. The second ball has a mass of 0.26 kilograms, it's more massive, and is moving with a velocity of 0.54 meters per second straight to the right. They collide with one another. After the collision, the second ball, the blue one, has a velocity of 0.7 meters per second. It looks like it's traveling 35 degrees below the positive x-axis. I missed a piece of information in there. And what we want to do is determine the velocity of the first ball after the collision. So we need to know is two pieces of information. How fast is the ball moving, Vf1, and the direction the ball is moving, theta. So this is a two-dimensional problem. What I want to do first is find the x and y components of momentum. My main solution technique here will be to separate everything into the x direction and the y direction and treat them as two different problems. This is very similar to when we dealt with forces, and very similar when we dealt with the two-dimensional kinematics problem. Separate the variables, treat them independently. So here are the x and y components of the momentum. For P1 initial, I have m1 v initial 1 sine of 50, really this side of the right triangle. And for the second one, I have m2 v initial 2, and it's all moving in the x direction. For object 1, m1 v final 1x, and for object 2, m1 v final 2 times cosine of 35, because I'm looking at this side of the right triangle. If we look at the x side of things, really the only thing I don't know is this thing here. For the y side of things, I could break up this vector into its y components, negative m1 v initial 1 cosine of 50. The blue ball has no momentum in the y direction to begin with. For the red ball, m1 v1 final in the y direction, basically this side here. And for the blue ball, negative m2 v final 2 sine of 35, because we'll be looking at this side of the right triangle. So those are all the components of momentum. And what I can do is apply conservation of momentum in both the x and y direction. Initial momentum in the x direction should equal final momentum in the x direction, and initial momentum in the y direction should equal final momentum in the y direction. So I take these two and add them up, and they should be equal to these two added up. Take these two and add them up, should be equal to those two added up. So here we go, we have my x and y equations, and I put x up here and y down here. What I can do now is solve for v final 1x and v final 1y. So here we go, here are the momentums. If I plug in the information I know, if I solve for what the final momentum in the x direction is for object 1, there it is. If I divide by object 1's mass, 0.15 kilograms, I get its x component of final velocity, 0.631 meters. I can do the same trick for y, plug in the numbers, calculate it out, find the final momentum in the y direction, solve it out, and find the y component of its velocity. So I've now found the x and y components of the red ball's final velocity. What I now need to do is use these components to resolve the vector. There's the x component, there's the y component, and so to figure out the final velocity, that looks like Pythagorean's theorem. It's like 0.642. To find the angle, I'm going to do tangent of this angle equals opposite over adjacent. And so the angle is 10.5 degrees. And so I could say the final velocity of the red ball is 0.642 meters per second at an angle 10.5 degrees above the positive x-axis. So the main trick to doing a two-dimensional problem is to break everything up into x and y, treat x and y independent of one another as you do the problem, and resolve the vector at the end if you need to resolve the vector at the end. So that concludes our lessons on momentum and collisions. So we've done one-dimensional collisions, two-dimensional collisions, impulse and momentum theorem. That should be what you need to know for this topic.